Well, I hope everyone enjoyed that teaser footage. Today we're talking about the aerodynamics of the RC Hypercar. The biggest goal of the RC Hypercar project is insane downforce. Tentatively, I want the car to be able to pull 3+ lateral Gs at a very tame 60 miles per hour or 100 kmph. And this is quite the challenge as aero forces increase exponentially as a square with velocity. So a car going 60 miles per hour only generates 1/4 of the downforce it would at 120 miles per hour. The wings and the aero devices on this car have to be absolutely massive to be able to generate downforce at this speeds. And to make matters more challenging, any weight I add from the wings or aero devices adds weight to the car, which means I need to add more downforce to compensate. Also, contrary to internet folklore, downforce to tractive force is not a linear relationship due to tire deformation, particularly RC car tires, which are not a pneumatic tire. So based on the initial testing, the RC Hypercar needs to generate roughly 2.5 to 3 times its weight in downforce, or roughly 14 pounds or 6.4 kilograms to reach that goal of 3 lateral Gs. There's a lot of information to cover when I'm going through the aerodynamics here on the car, and I'm going to try to break this up over a few videos. The entire design and development process for the RC Hypercar aerodynamics took the better part of a year. This video is a very brief introduction to aerodynamics and CFD, and then I'll actually cover the aerodynamic development around the underfloor and the diffuser of the Hypercar, and in the later videos I'll get into the front wings, the rear wings, and then some of the actual aero mapping and aero sensitivity testing that we've done. Quick disclaimer, I'm not an expert in the field of aerodynamics. If you want to know more about the subject, I highly recommend consuming everything written by Joseph Katz or F1 designer Willem Toet. To kick this off, I'll touch on some high-level key concepts of the dark art of aerodynamics to hopefully allow more of you to be able to follow along in these videos. First, to create downforce, you need to create a pressure differential in the air between two surfaces. So when designing a car, you want high pressure on the top of the car, pushing the car down, and ideally low pressure on the bottom, sucking the car to the pavement. This bloke named Bernoulli discovered that the faster air flows, the lower its pressure, and conversely, the slower the air, the higher its pressure. So we can use this rule to actually shape the car so that as much of the slow air is on top of the car and the fast air is going to be on the bottom of the car. The other important thing to know is air desperately wants to reach a pressure equilibrium. So if there are two areas of differing pressure, the higher pressure air will always flow towards the low pressure air. When high pressure air falls off an edge, trying to get to that sweet low pressure zone, you create a vortex or a bit of spinning air, and we'll be talking about vortices a lot as they have a lot of uses and some drawbacks in race car aerodynamics. I'll also probably mention the boundary layer a lot. To keep this as non-technical as possible, think of air as a sticky substance like honey. As it flows over the surface of an object, the layer of air closest to the surface tends to stick to that surface, and the layer of air where the velocity drops to near zero is called the boundary layer. If the boundary layer gets too thick, the air can actually fall off the surface in big low energy blobs, and this is called flow separation, which can ruin how an aerodynamic device actually performs. The next concept I'll talk about a lot in the videos is ground effect. Ground effect is when you bring an aerodynamic device such as a wing close enough to the ground that the ground itself helps to block that high pressure air from traveling under the aero device, greatly increasing the efficiency and effectiveness of the aero device. So to design and evaluate the aerodynamics of the Hypercar, we're using something called computational fluid dynamics, or CFD. CFD works by dividing or meshing the area around the car into millions of tiny little cells. And computers can then apply a variety of different solver methods to calculate the airflow and pressure through the cells. Obviously, the more cells you have, the better the resolution of your CFD results, but the more computational time it requires. So basically you want to strike a balance between your accuracy needs for your particular application and the amount of processing time required to calculate all those cells. The one topic that always comes up when you're talking about CFD is, are the numbers coming from the CFD simulation absolutely accurate to the real world? And no, but they're very close for most circumstances. CFD is excellent for doing back-to-back comparisons in a controlled environment between different design choices, visualizing the interaction of different aero devices, and even aero balancing the car. While CFD is not perfectly accurate, it's orders of magnitude more accurate than human intuition will ever be. So to kick off the design process, I started sketching simple designs for the body based on existing race cars I had studied. From this, I built some simple models to try to run through the CFD software to see how they performed. I did not get this right the first time. I did over 800 CFD simulations trying out different designs and aero devices and aero concepts. It was a great way to learn how race cars actually worked, but the aero concepts didn't always translate well to what I was trying to do with the RC Hypercar. And that's primarily because most race cars have to follow a rule book. And rule books limit the number of wings, how tall or wide a wing can be, how close a car can be to the ground, and all sorts of other annoying things. So from what I've learned on this journey, I've formulated a few guiding principles around aerodynamic development. For the RC Hypercar, weight is actually usually more important than downforce, and downforce is almost always more important than drag. Weight is bad at every speed. At a certain size, the wings and the aero weigh more than the actual downforce they generate, particularly at 40 miles per hour or less. So that means having a lighter weight car makes the downforce that you do generate much more effective. And within reason, drag doesn't matter because the car has more than enough power. It's really overpowered when you look at RC cars compared to even full-size race cars. It does affect battery life, and the motors currently pull over 600 watts at 60 miles per hour. So heat is also a factor. So, reasonably you want to keep drag within check, but it is by far the lowest on the list compared to weight and downforce. I also found race car designers spend a lot of time trying to optimize that last 2 to 3% of aero performance to fit within the rules they have to work with tiny flicks and winglets and all sorts of other little aero bits and bobs. These small aero devices make very little difference, and they require a lot of computing power to simulate. I've learned that if the rules allow it, big, smooth, simple aero devices are the most effective and efficient. Next, I think it's very important for this car to have as large of an operating window as possible. I mean, this is a scale RC car that'll be operating in far from ideal conditions. This car is much shorter than a full-size car. It's driving on rough surfaces. The car is going to pitch and roll at angles much larger than those of a full-size car. So it's important the car doesn't lose half its rear downforce when making a turn and becoming completely unstable. Lastly, the order of design and optimization of your aero devices is very important. So I initially designed and roughly optimized the largest aero device, which is the underfloor. Once I had that worked out, I worked from the front to the rear of the car. This is important because it's very easy to design an aero device at the front of the car that makes more downforce at the front, but subsequently ruins the aero performance downstream. Then once I had the rough design, I tried to balance the downforce between the front and rear. The balance in the downforce on the front and the rear has to roughly match the weight distribution of the car. I do have a little additional downforce in the rear just for stability because I find it's easier in high-speed turns to have understeer rather than oversteer. And then it's just endless loops of optimizing and looking at the interactions between the various aero devices to try to eke out that performance and find little places you're finding flow separation, you're finding places where there's drag, you're finding aero devices that are not necessarily in the optimal placement for the airflow. So I did a lot of work around that, and I'll talk about those in more detail as we go through each of the air devices individually. So before we launch into this, I want to just talk a minute about CFD software. Most CFD software packages are tens of thousands of dollars, if not hundreds of thousands of dollars. So about a year ago, I started trying to find the best free CFD software. I messed around with a bunch of different CFD packages. Ultimately, none of them worked very well or required a lot of money to unlock the features that I needed. So initially, I chose the path of pain, and I used a very powerful open source CFD software called OpenFoam. In particular, I used Blue CFD, which is a version made for Windows. Unfortunately, there are no free user interfaces for OpenFoam, so using it involves hand editing dozens of text files, writing custom scripts, and knowing a lot of the intricacies of how aerodynamics work to manually configure all of the parts and pieces of OpenFoam. It's also very fragile, and you end up battling endless vague error messages before you can get a simulation actually running. Then I found a company called AirShaper that has a wonderfully easy to use cloud-based CFD product. Literally within 30 minutes of uploading my model, I had the results from my first CFD simulation. The process is super simple. You upload an STL model of the car you want to run the simulation on. The model does not need to be perfectly watertight, which is great. It is recommended you pre-orient your model in something like Mesh Mixer or in your CAD software to be oriented properly within AirShaper, and then also cut the bottom of your tire so that you have a nice contact patch so that you can simulate that as well and you have that nice flat spot. Then you configure some basic parameters for the simulation like airspeed and fluid type. Obviously, if you're a CFD expert, you're probably used to manually configuring your different solvers, turbulence models, patches, and meshing methods. And I'd love to be able to tweak some of those settings like in an advanced user menu. But the reality is AirShaper has done an excellent job handling all that complexity in their software automatically. Once you have the simulation configured, then you can pick the level of simulation you want, which is a combination of the number of cells, some additional features like spinning wheels, and additional reporting data as well. For the RC Hypercar, I used the basic simulations, which are just 50 euros each for 99% of the aero development and optimization. I did reach out to AirShaper asking for help with the CFD for this car and for the videos, so I was able to run some additional, more advanced simulations and get valuable feedback from the founder of AirShaper, Wouter Remery. The downforce numbers really didn't change materially between the basic simulation and the more advanced simulations, but things like the underfloor vortices or the complex flows around the wheels definitely became much clearer and nicer for visualization if you have to optimize those particular areas on your car a lot. AirShaper has some cool online reporting, or you can actually download the data to create your own reports and visualizations in the industry standard free software called ParaView. So I want to start with the underfloor because this area has the ability to generate a significant amount of very efficient downforce for the car. This picture here is a coefficient of pressure rendering of the RC Hypercar's underfloor. The coefficient of pressure is very similar to like a coefficient of drag, where it's a unitless way of measuring pressure so that we can easily compare two pressure plots against each other relatively so that the colors and everything align. Because I wanted to maximize the downforce and limit the aerosensitivity of the floor, we have two long and very deep venturi tunnels that take the air in here at the inlet and compress it along its length until it reaches the throat of the diffuser, which is the narrowest bit of the diffuser, and then expands the air as quickly as possible through the outlet. This creates a low pressure zone at the throat of the diffuser where the air velocity peaks. Now, this particular diffuser looks a little bit different than that, and I'll go into why that is. So this here is the side profile of the diffuser, and it's actually what's referred to as a double kicked diffuser. This is a common diffuser design used in a lot of race cars. The first kick-up or throat point is just ahead of the rear suspension so that we can generate some downforce further ahead on the car. And then the diffuser is actually straight for a bit where the rear suspension mounts to the monocoque, and then it kicks up again after the rear suspension has been cleared. This isn't always as efficient as a single kick-up point diffuser, but it does help to balance the aero downforce on the car, and the first kick-up point is not as badly affected by the tire squirt or the wake coming off of the rear tires, which can be beneficial. You can see the venturi tunnels don't come all the way to the bottom of the floor, even at the throat. I did this on purpose to lessen the aero sensitivity of the floor. The ratio between the cross-sectional area of the throat and the outlet of the diffuser is called the diffuser's expansion ratio. The larger the expansion ratio, the larger the potential for generating downforce, as long as the air still remains attached to the diffuser, i.e. the boundary layer doesn't become too thick. This generally means a well-designed diffuser can have an expansion ratio of around 1 to 6. The lower the vertical height at the throat, the more sensitive the downforce becomes to ride height. I have two example diffusers here, both with the same stock expansion ratio of 1 to 5. The first diffuser only has 3 millimeters of height at the throat, and the second diffuser has 9 millimeters. Obviously, you need a bigger outlet to have the same expansion ratio. Again, I'm not limited by rules, so I can have that bigger outlet. But what's interesting is when you drop the ride height by only 1 millimeter, the smaller 3 millimeter throat height diffuser goes into stall with a 1 to 7.5 expansion ratio. It's actually just 1 millimeter has a 50% increase in expansion ratio. Whereas with diffuser number 2 and the taller throat height, you can see that 1 millimeter change in ride height only changes the expansion ratio by 20%. And you can see from this is why you have the effect of porpoising in F1, because they have a limit to the size that their diffuser can be, so they're going to try to push that throat height as close to the ground as possible, which means the diffuser is closer and closer to that state where it's potential for it to stall to be able to maximize the performance of the diffuser. This is a view looking at the top of the diffuser profile, and you can see the diffuser's horizontal expansion, meaning we can actually make the diffuser narrower at the throat widthwise and then wider at the outlet. This is the best thing for diffusers because horizontal expansion is not ride height sensitive. Most race cars have a limited amount of horizontal expansion because of rules or because of physical packaging between the tires themselves. So running on the edges of the floor here have some really important aero devices, which are these flexible edge skirts. The underfloor generates a lot of low pressure over a really big area. Unfortunately, because it's such a big area, that means there's a lot of space along the edges for the high pressure air above the diffuser to leak under the floor and ruin the efficiency of the diffuser. So most full-size race cars run very close to the ground to minimize this effect of the edge seal leaking, or they run different vortex type sealing structures. But this being an RC car, I need orders of magnitude more ground clearance than a full-size car needs. So the flexible edge seal allows me to run the car basically touching the ground at speed. The shape of these edge seals helps to kick up the air as it comes over the top of the floor edge, and I have two separate vortex generating tube structures. These vortex generating tubes will help to spin the high pressure air that's trying to leak under the floor, and it'll actually form an air curtain that will help to seal that floor better from that high pressure. So the edge seal is something I designed myself, and it's still a work in progress, but I can tell you that the edge seals themselves more than double the downforce coming from the underfloor. Another feature of the underfloor is we have some vortex generating tubes right here next to the rear tires to help minimize the wheel wake or the tire squirt being spilled into the diffuser. Additionally, we have two strakes which help to compartmentalize the losses from the rear wheel wake. If you want to check more about this, Kyle.Engineers has a great video on diffuser strakes and their functions. So I'm not 100% sure what the ideal number of strakes for the underfloor are, but 4 strakes makes very little difference compared to 2 strakes and drastically increases the drag. So I went with 2 strakes. Okay, so the last interesting bit about the floor, as you can see from the pressure maps, is that there is downforce being generated across almost the entire floor. And this is really ideal, and it's not always achievable because of those pesky rules. But the reason we have downforce over the entire floor is a combination of the giant rear wing and inlet vortex generators. The rear wing and gurney at the back of the body actually help to create a massive upward flow at the back of the diffuser, which actually draws the air through the underfloor. I think of it like a giant vacuum cleaner sitting right there behind the diffuser. I spent a tremendous amount of time optimizing the placement of the rear wing, and the lower and further back the rear wing was, the more effective it was at helping the diffuser. But if it was too far back, it would upset the balance of the car and might cause the nose to lift. It also would lose some performance by getting less air back there. And then here at the inlet, we have these 3 vortex generators. These vortex generators do a few things. They help to energize the air coming into the diffuser by creating a nice set of 3 smaller vortices, which almost instantly join together to form a pair of counter-rotating vortices on each side of the diffuser. These vortices keep the boundary layer thinner at the throat and help promote flow attachment and decrease the sensitivity for the diffuser as the car pitches and yaws. And the vortices, because they're spinning and have a lot of velocity, they're actually causing something called vortex-induced low pressure. And that whole discussion is way above my pay grade. I'm not an aerodynamicist, but the vortex generators actually allow the diffuser to generate more downforce and generate this downforce further forward. And I'll link to some research papers that were done by Joseph Katz in the comments regarding these vortex generators. I mean, you can see how these 2 vortices run the entire length of the diffuser, and then this cool 3D contour picture shows just how powerful the vortices are as they come out of the diffuser, are deflected further up by the rear wing, and then go back out behind the car. I spent a significant amount of time optimizing the shape of the diffuser and these vortex generators, tried different numbers of vortex generators and different angles and different methods for creating the vortex. The shape is very important. You want to bring the air in gently and then kind of at the last second curve it in a harsh manner so that you get the vortex to form at the end of the vortex generator. There are a lot of rules of thumb of how to design a diffuser, but ultimately it really is kind of a trial and error process. You know, I'll come up with an idea, I try it out in CFD and see whether or not that idea improves the performance of the underfloor. Probably 70% of the time it does not improve the performance, and that 30% of the time it does. There's a lot of times that the underfloor changes don't make sense, and so I spend a lot of time trying different variations. Like, for example, this particular diffuser, I should be able to have a additional horizontal expansion. The flow is nicely attached, but I'm not getting additional downforce from that additional horizontal expansion. So, you know, you just design it to what is most efficient and kind of where the CFD points you. Obviously, there's optimizations that could probably be done with a wind tunnel or some additional testing in the real world, but I think we're going to more than exceed downforce figures for what the performance goals are for this car. The CFD is saying, you know, we're going to generate over 8 kilograms of downforce, and I can tell you in testing right now that the car is bottoming itself out, even with the suspension that's probably can handle right around 5, maybe even 6 kilograms of downforce. And that's going to be a significant issue to address, because once the car bottoms out, you essentially, your downforce isn't working for you any longer. You're just pushing the body of the car into the ground. I think that wraps it up for this video. I think this video is already pretty long and have a lot of content in there. In the following videos, I'm going to really focus on the overall shape of the body itself, the wings, the dive planes, and some of the other aero devices that are on the upper side of the body. And then the last video, I'll talk a lot about aero sensitivity and aero mapping for this car, because that's hugely important to make sure that this car can maintain its downforce in a variety of different attitudes and conditions. So let me know in the comments if you guys have any questions, or if there's anything that I didn't cover that you want to see covered in more depth. Like I said, that wraps it up for this video. I just want to thank AirShaper for helping me out with the CFD and with some of the design on the RC Hypercar. Until next time, stay safe out there.